Today, let us discuss some assertion recent questions related to the quadrilaterals. We have two statements here. First, we have to check if both are correct. Now, what are the statements about? They are about two different kinds of quadrilaterals. One a rectangle, another one a parallelogram. How are they related? Every square is a rectangle and every rectangle is a parallelogram. Similarly, every square is a rhombus and every rhombus is a parallelogram. But as you see, the arrow points only in one direction, which means the equality also works only in one direction. Every parallelogram need not be a rectangle. Now comes the important question. How do we get this relation? Why do we classify quadrilaterals as square or rectangle? How do we classify them? Now, all you know about a quadrilateral is that it is a four-sided polygon and all of its angles together add up to 360 degrees. Now, based on the properties of three things related to any quadrilateral, what three things? Its sides, angles and its diagonals. Based on their properties, we classify them into different types. Here itself you have four types, a square, a rectangle, a parallelogram, a rhombus, and you have studied two more, a trapezium and kite. Right? So, based on the properties of these three things, we classify them into different groups. Here our question is about diagonals, so we will stick to diagonals. So if ABCD is the name of your quadrilateral, remember that AC and BD will always be the diagonals. Even if you do not have the figure, remember the vertices move in a cyclic order. For the diagonal, you have to miss a vertex. Jump over and then you will get the diagonal. AB will be what? It will just be your side. Even without the illustration, you should know that AC and BD are your diagonals. Now look at the conditions that we have written down. This should explain the whole scenario. What is happening here? Parallelogram. The diagonals of a parallelogram have a minimum condition to satisfy. Rectangle, a bit more. Square, even more. So the more conditions that you have to satisfy, the more difficult it is to be that figure. For example, parallelogram is just like ordering a plain coffee. Somebody comes to your house and asks for a plain coffee. It is very simple. But then when you give the person coffee, then he tells you, you know what, not just coffee, I need it in a blue cup. And now you have to arrange for a blue cup. By the time you give it in a blue cup, that person says, you know what, blue cup and a red saucer. At that point you will say, you know what, get your coffee yourself. Because the more conditions you have to satisfy, the more difficult it is going to be that figure. Now look at the parallelogram. What do you have to have? It just has to bisect. The diagonals just have to bisect each other, which means if one diagonal is say 20 and the other one is 14, then all the diagonals have to do is cut each other into two equal parts. That is all you need to do. Now, when it comes to rectangle, you have another condition. It cannot be 14 and 20. They have to be same. They have to be 20 and 20, which means what? You have four equal parts here. Now, when it comes to square, even this is not enough. Even the diagonals being same is not enough. They have to meet each other at right angles. So, here a 90, here a 90. All the four angles is 90. In these cases, it is not necessary that it is 90. For example, this, it is enough if this is 40. If this is 40, what will be this? The vertically opposite angle? This will also be 40. Then, if you see this as a straight line, if this is 40, it will be 140 here, 140 here. All you need is for them, when it completes the circle, when it completes the revolution, it should be 360. Vertically opposite angles must be equal. So you can have a 40, 40, 140, 140. But that is not going to work with a square. Each angle has to be 90. So now look at the figures again. You see why every square is a rectangle and every rectangle is a parallelogram, and it need not happen the other way. Now let us come back to our question. What does the question say? The diagonals of a rectangle are equal. Is it correct? Yes, it is correct. Diagonals of a parallelogram bisect each other. Is it correct? Yes, it is correct. So both the statements are correct. Is the second statement the reason for the first? No, not in any way. Both are correct, but it is not the same. Our next set of questions, diagonals of a rectangle are perpendicular to each other? No, they are not. What about the second one, diagonals of a rhombus bisect each other? Yes, they do. And how do they bisect? They bisect at right angles. So the second statement is correct, the first one is wrong. Now look at this question. If the diagonals of a parallelogram are equal, then it is a rectangle. What do we have here? What is stopping the diagonal of a parallelogram from becoming the diagonal of a rectangle? You have already one condition satisfied. You just have to satisfy the second condition. If that is satisfied, the diagonals of a parallelogram are equal. If this condition is also satisfied, it means what? The parallelogram can behave like a rectangle. So the first statement is correct. What about the second statement? Diagonals of a parallelogram bisect each other? Correct. But then, is this the reason for the first statement? The answer is no. Then what is the reason? For that you have to understand what are the differences in the angles between these three figures. Shall we move on to that? First we saw how the diagonals of these four figures are different. Now we move on to the angles and let us see how the properties of the angles are different. We start with the most basic figure among all these four. The four of them, the most basic figure is the parallelogram. It satisfies just a basic set of rules. Same with angles. What is the basic rule that it has to follow? The angles, the opposite angles should be equal, and the adjacent angles should add up to 180 degrees. That is all. It's very simple, right? But then what about the rectangle? This is not good enough. Each angle has to be 90. 40 and 40 is not good enough. Each one has to be 90 degrees. And that itself is the reason for this. Now we come back to our question. Both the statements are correct, but the second one is not the reason. What we mean is that it is not the direct reason. There is one more step to be done. What we have to prove is that if the diagonals of a parallelogram are equal, then we can prove that one angle is 90. That is enough. If you have a parallelogram and you prove one of the angles is 90 degrees, that is enough to prove that that figure is a rectangle. Why is that? If one of them is 90 degrees, then its opposite side will be 90 degrees here, because opposite sides equal. If this is 90, then the adjacent side will be 90 degrees. There you have. Then if just one angle is 90, that means all the four are 90. That means your parallelogram is a rectangle. Now this is the reason. If you have a parallelogram and one angle is 90, then it is a rectangle. This is the direct reason. What you have here, will lead to that direct reason. How will it lead to that reason? Look at the look at the diagonals. If they are equal, they will cut each other into 4 equal parts. Now consider this triangle. If these two sides are equal, then this will be x and this will be x. Suppose this is y, you have a parallelogram, which means what? Alternate interior angles are equal, which means what? If this is y, this is y, again you have 2 equal sides. That means their opposite angles are equal. There you have. What do you have? The 2 adjacent angles. One is x plus y, the other is also x plus y. You have 2 equal angles here, both of them. If 2 angles add up to 180 degrees, then each one has to be 90. So from this step, what you can prove is that one angle, both these angles are 90 degrees. That means the other ones are also 90 degrees. So you have a rectangle. Not a direct reason, but something which leads to this. So this brings us to the next set of questions, which connects your diagonals and the angles. Now look at this question. What do you have here? You have a quadrilateral. You have no idea if there is anything special about it. Is it a parallelogram? Is it a square? You have no idea if there is anything special about this quadrilateral. Then, to prove that it is a parallelogram, any one of these 4 conditions must be satisfied. There are 4 conditions here. Take the first one, the diagonals, if they bisect, it is a parallelogram, and it is what we call a if and a only if condition. It is often referred to as IFF. It means if and only if. That means if it is a parallelogram, diagonals will bisect. If the diagonals bisect, it will be a parallelogram. The conditions work both ways. So if this is a parallelogram, this will be true. But if this is true, that is enough to prove that ABCD is a parallelogram. This is one condition. What is the second condition? You don't know anything about the diagonals, but you do know about the angles. You know that A and C are equal. You know B and D are equal. That is enough. If you can find that, then again this will be a parallelogram. Now you have no idea about the diagonals, no idea about the angles. All you know is about the sides. If you can prove both the pairs of opposite sides, AB and CD are equal, AD and BC are equal, if you can prove that, then again this will be a parallelogram. Now you don't know that also. You do not have any information about both the pairs, but you do know about just one set. You just know that this AB and CD, you know that they are equal and they are parallel, then that is enough. Do you see how flexible this condition is? Diagonals, if you don't know that, angles, if you don't know that, sides. If you don't even know that, just take one pair. That is enough to prove that this is a parallelogram. Now we come to our statements. Look at the first statement. Diagonals of a quadrilateral bisect each other. Then what do you know? It has become a parallelogram. If it is a parallelogram, look at the 2 adjacent sides. A and B adjacent. They come nearby, which means their sum should be 180 degrees. Is it 180? Correct. So the first thing is correct. Look at the second statement. Diagonals bisect each other. That is enough. It is a parallelogram. Is it true? Again correct. Is this the reason? Again correct. So both are true, and the second one is the reason for the first one. Now this is a very important question related to the diagonals of a rhombus. Now what is the basic property of the diagonals of a rhombus? All you know is that they bisect each other perpendicularly, which means what? The place where these 2 diagonals meet, that place cuts them both equally and at right angles, which means all the 4 places will be right angles. These 2 set will be equal, and these 2, AO and OC, will be equal. BO and OD will be equal. That is the basic set. Now this is an added, it is a bonus. What do you get? The diagonal AC cuts the angle A and C, both of these angles, into two equal parts. Now you have to show that these two small angles are equal. Now what you have to prove is that BAC and DAC are equal. Let us not go all the way. Let us just stop here and take two small triangles and prove that they are congruent. Are they congruent? Take AOB, AOD. Is the angle equal? Both are 90 degrees. Why? Because the diagonals of a rhombus are perpendicular. AO is the common side. What about AB and AD? These are the sides of a rhombus. All the four sides of a rhombus are equal, which means what? By RHS criterion, both of these triangles are congruent, which means both of these angles are what? They are equal. Or in other words, you have AC cuts angle A into two equal parts. Now repeat the same thing here with a different set of triangles. Now take BOC and BOC. Again you can prove these two angles are equal, which means what? The diagonal cuts it into two equal angles. Now is the first one true? We have just now proved. Now you can repeat that with the second set also. Is the second statement true? Correct. Is the second statement the reason for the first one? Yes. Now we have had an overdose with diagonals. Let us take a break. Come to the next thing which is related to the quadrilaterals. What? The angles. We will see in next few questions about the angles. This is the first one. Can all the angles of a quadrilateral be acute? Acute means what? It must strictly lie between 0 and 90. What do we mean by strict inequality? Which means it is not greater than or equal to, or here you will not have the equal to sign. It can never be 0 or 90. Now, can all the four angles be acute? Randomly take any one angle here. I will take the greatest. I will take say about 80. Can all the four angles be 80? If all the four angles are 80, then what will I get? I will add them and I will get only this much. But then the sum of the angles of a quadrilateral are what? They are 360. So this is not true. This is true. Now the same question can be asked in a different way. Can all the angles of a quadrilateral be obtuse? What do we mean by an obtuse angle? It should strictly lie between 90 and 180, which means what? 90 is not included. This figure is not included. This figure is not included. It should lie directly, strictly between these two. Randomly give me a number which is what? Say, I will take 100. So 400 is going to give me what? It is going to give me 400 degrees. Then is that possible? No. Again the same thing. First statement not true. Second statement is true. Now we move on to the next set of questions, which is about what? The midpoint theorem. It is actually related to a triangle, but we use it a lot when we come to the quadrilaterals, because if you see the diagonal of any quadrilateral, it will cut the quadrilateral into triangles. So we need this theorem. This is very important theorem. What does it say? You have two different parts of the theorem. One is the main theorem and the other is what? It's converse. What does the main theorem say? You have a triangle here, ABC, and you have the midpoint of AB and AC. You have the midpoint. Then if you join this midpoint, this line that you get, this is a very special line. What is special about this line? It is half of BC, which means if BC is 10, this is 5. And what else is special about it? This line will be parallel to BC. What do you mean by parallel? All the rules of the two lines being parallel and the transversal cutting them, all of that you can apply here. What all? The alternate interior angles, the corresponding angles, whatever rules you have, all of that you can apply here. That is what is special about this line. So the main theorem is about what? Two midpoints and the line joining them. And what is special about this line? What does the converse say? It is slightly different. You do not know the midpoint of this line. You only know the midpoint of one of the sides. You know what is the midpoint of A. That is all you know. Then through that E, if you draw any line, all that line has to be is parallel. If from E you draw a line which is parallel to BC, then the place where it goes and meets, this will be the midpoint. Now look at the question. What does the question say? What does the second statement say? Line through the midpoint of one side parallel to the other side intersects the third side at its midpoint. Is it true? Yes, it is. It is exactly the converse of the midpoint theorem. Now let us come back to our original statement. The second statement is true. It is the converse of the midpoint theorem. Now let's come to the first statement. What is the first statement? You have a triangle. AD is the median. What do you know about the median? The median will start from one vertex, go to the opposite side and cut it into two equal parts, which means what? D is the midpoint. Now E is the midpoint of that median, which is what? It is given here. Now what you have to prove is that this AF is 3 times AC. We will find some way to connect E and D so that we can apply the midpoint theorem. How do we do that? What about we consider this triangle BFC, right? It includes both what? E and D. But then to apply the midpoint theorem, what do we have to do? We have to draw a line from one side to another. What if we draw a line like this? So now consider this triangle BFC. You have here midpoint. From midpoint you have constructed DP parallel to EF. So we see that BF and DP are parallel to one another, and this line DP, it passes through D, which is the midpoint of BC. Then what is the only option left? If it is parallel, it has to go and meet in the midpoint. There is no other way. P has to be the midpoint of FC. That is what the converse of the midpoint theorem states. So now you have what? P is the midpoint of FC, which means what? FP is equal to PC. We have proved that these two sides are equal. Now we have just proved this one set, right? Now let us move on to the next set. Can you think of any triangle which will include AF and FP and have a midpoint of one of them included? It will be ADP, right? Why? The way we have constructed it, DP was parallel to BF. It was, if it is parallel to the whole line, it will be parallel to just a part of it also, right? It was parallel to the whole of BF. So just take a part of BF, which is what? EF. It is parallel. And you have E is what? The midpoint of AD. Now you have a line going from the midpoint parallel to the third side. Where will it go and meet? What is the only option left? F has to be the midpoint of what? Of AP. It has to be. There is no other way. So if F is the midpoint, then this is also equal, which means what? AF is equal to FP is equal to PC, which means what? 3 times AF is equal to the whole of AC, which means AF is equal to 1/3 of AC. That is exactly what our first statement is. And how did we prove it? Did we use the converse of the midpoint theorem? Yes. At every point, to prove this is the midpoint, then to prove this is the midpoint. In both the cases, we have used the converse of the midpoint theorem. Please be careful. If in the reason you are given the original midpoint theorem, then that is not the reason. In both the cases, what we have used is its converse. So please be careful when you see the reason. Is the reason what you have used to prove the first statement? Only then it is the right reason. So both are correct, and this is exactly the reason. Again, the similar question but slightly different. Here also the second statement was the converse of the midpoint theorem. Now you have to prove this result. What do you have? You have two medians. One median is AD. What does that mean? It meets in the midpoint of the opposite side. So B is the midpoint of BC. BE is also a median, which means what? The place where it goes and meets is the midpoint of AC. Now consider this very small triangle. What do you see? You know the midpoint of one of them. You are seeing a parallel line. Then the place where the parallel line goes and meets, that point has to be the midpoint. That is what the converse of the midpoint theorem states. Now, if F is the midpoint, what does that mean? EF and FC are equal, which means what? FC is just half of EC. But then, what is EC? E, it is what? Given as a midpoint of AC, which means EC is half of AC, because it is a midpoint. Instead of that, you can put it there, you can substitute it there, or in other words, you will get AC by 4.